Have you ever really stopped to think about what's inside your phone or your laptop? What makes it all work? Well, it all comes down to a tiny, unbelievably powerful little device, engineered from one of the most common things on the entire planet, sand. So let's dive into the incredible story of the semiconductor revolution. All right, so here's our roadmap for this explainer. First, we'll take a quick look at the world before semiconductors, a world of giant, glowing machines. Then we'll zoom in on the just right material that changed everything. After that, we get to the really clever part, how we hack that material to create a one-way street for electricity. And finally, we'll see how that one simple trick is the reason every single gadget you own actually works.
You know, to really appreciate the magic of the tiny silicon chips we carry around in our pockets, we've got to jump in a time machine. Let's go back to the age of the vacuum tube.
I mean, this slide just says it all, doesn't it? On the left, you've got the old world of vacuum tubes. These things were huge, they were fragile, they guzzled power like crazy, and they burned out all the time. But on the right, you have the semiconductor. It's tiny, it sips power, it's incredibly reliable, and it lasts for ages. This wasn't just an upgrade, it was a complete game changer.
So what exactly makes a semiconductor, well, so special? It really all boils down to one simple property: how well it lets electricity flow through it. So think of it like this. On one extreme, you have materials like copper, metals, that let electricity flow almost perfectly. They're conductors. On the other extreme, you've got things like rubber or glass, insulators, that block electricity completely. And right there in the middle, in this perfect Goldilocks zone, you find semiconductors. They're not too conductive and they're not too resistive. And that middle ground is exactly what makes them controllable.
And to understand why, we gotta look at something called energy bands. Now, in a conductor, like a metal, the home level for electrons and the freeway level where they can move around and conduct electricity are basically right on top of each other. They're overlapped. So electrons can just wander around freely conducting current with almost no effort.
Now in an insulator, it's a totally different story. There's this massive energy gap between those two levels. It's like the staircase to get to the freeway is completely missing. The electrons are just stuck where they are. No matter how hard you push them with voltage, they can't make the jump. No current flows, period.
And this is the secret sauce. A semiconductor has a gap, but it's a small, manageable one. The staircase is there. It just takes a little bit of a push, a little energy boost from a voltage, to get the electrons to climb up to that conduction freeway. It's this small gap that gives us the power to control the flow, to turn it on and off like a light switch.
Okay, so having this controllable material is a fantastic start. But the real genius move, the breakthrough, was when scientists figured out how to hack it, how to tweak its properties with incredible precision. And this process has a name: doping.
Doping is basically a form of high-tech alchemy. You take a crystal of ultra-pure silicon, and you intentionally sprinkle in a tiny, tiny amount of another element. And when I say tiny, I mean we're talking about maybe one impurity atom for every million silicon atoms. But that tiny change completely transforms how the silicon behaves electrically.
And this lets us create two different flavors of silicon. On the one hand, if you add an element with one extra electron, like phosphorus, you get what's called N-type silicon. The N is for negative, because you have all these extra free electrons wandering around. On the other hand, if you add an element that's missing an electron, like boron, you create these little vacancies called holes. We call this P-type silicon, because these holes act just like positive charges. And you really have to get this because this idea is everything. We can now make materials where the main things carrying the charge are either negative electrons or these positive holes. This distinction is the absolute key to building, well, just about every electronic device we have today.
So now we have our two custom-made types of silicon, one with extra electrons and one with extra holes. So what do you think happens when we bring them together? Well, this is where the real magic begins.
The moment these two materials touch, physics just takes over. All those extra electrons on the N side see the empty holes on the P side, and they just can't help themselves. They rush across the boundary to fill them in. And as they do that, they leave behind positively charged atoms and create negatively charged atoms on the other side. This creates a built-in electric field right at the junction.
This little zone right at the boundary is called a depletion region, and it acts like a tiny invisible force field. That internal electric field it creates pushes back against any more electrons trying to cross.
It's an automatic barrier that stops the flow of charge cold.
Okay, so we've got this automatically forming wall. So what? Well, here's the cool part. We can use an external battery to control that wall. We can either shrink it down to nothing, or we can make it even bigger and stronger. Check this out. If we hook up a battery in one direction, we call this forward bias, we basically push the electrons and holes towards the barrier, shrinking it and letting current flow right through. But if we flip the battery around, reverse bias, we pull the charges away from the barrier, making it wider and stronger, blocking the current completely. We've built a one-way street for electricity.
And hey, if you don't believe me, the data tells the whole story. Look at this graph. When we apply a forward bias voltage, whoosh, the current just takes off. But when we apply a reverse bias, nothing. It's a flat line, it's a perfect switch, an open door in one direction and a brick wall in the other.
Now, you might be thinking, okay, a one-way gate for electricity is kind of neat, but why is that so important? Why is this thing in basically every electronic device I own? Well, let me show you.
You see, the power that comes out of your wall socket is what we call alternating current, or AC. It's constantly flowing back and forth. But our sensitive electronics, they hate that. They need a smooth, steady, one-way flow called direct current, or DC. So we can use one of our diodes to chop off the negative half of that AC wave. It works, but it's super choppy, and we're literally throwing away half the power.
Of course, we can be much smarter about it. Using a clever arrangement of diodes, we can build what's called a full-wave rectifier. Instead of just chopping off the negative part of the wave, this circuit actually flips it over and makes it positive. Now we're using all the energy, which is great, but the output is still a pretty bumpy ride.
So for the final step, we need to smooth out those bumps. And for that, we bring in another simple component, a capacitor. You can think of a capacitor as a tiny, super fast rechargeable battery. It charges up on the peaks of those waves and then discharges during the valleys, basically filling in the gaps. And just like that, it smooths out the pulses into the clean, steady DC voltage that all our gadgets need to survive.
So let's just recap this incredible journey. We started with silicon, a simple Goldilocks material. We hacked it with a process called doping to create two different types. We slammed them together to form a PN junction, which magically acts as a one-way gate for current. And then we use that simple one-way gate to tame the wild electricity from the wall socket, turning it into the clean power that runs our entire digital world. And here's the really mind-blowing part. This simple PN junction, this one-way gate, is not just for making power supplies. It's the fundamental building block for everything. You stack them together in different ways and you get transistors, and the processor in your computer or your phone, that's just billions. Literally billions of those tiny transistors working together. It all starts right here, with this simple little junction. The modern world is quite literally built on sand.